Hello, Vital Sign. Today we're going to explore optimal graphs for domination polynomials. First, by G sub n e, we mean the set of all simple graphs with n vertices and e edges. A graph H with n vertices and e edges is said to be optimal for domination polynomials if for all graphs G in G sub n e and for all x greater than or equal to 0, the domination polynomial of h evaluated at x is greater than or equal to the domination polynomial of g evaluated at x. If there's only a single domination optimal graph in the set G sub ne, then we say that graph is the uniquely optimal graph for G sub ne. One scenario that would clearly produce a domination optimal graph would be a graph H in G sub ne such that the number of dominating sets of k vertices is greater than or equal to that for any other graph in G sub ne for all positive k. Also, we can compare the optimality of different graphs as long as they have the same number of vertices and edges. If we have two graphs, G and H, with the same number of vertices and edges, and if for all x greater than 0, d of hx is greater than d of gx, then we say graph H is more optimal than graph G. Note that for a graph to be domination optimal, its domination polynomial must be greater than or equal to that of any other graph of the same order and size, at both arbitrarily small positive values of x and arbitrarily large positive values of x. This will be important for our next two observations. Let G and H be graphs in G sub ne, and let little d of gk denote the number of dominating sets with k vertices in graph G, and little d of hk denote the number of dominating sets with k vertices in graph H. Our first observation is this. If little d of gk equals little d of hk for all k less than some integer L, but little d of gl is greater than little d of hl, then d of gx is greater than d of hx for arbitrarily small positive values of x. Intuitively, this is because the only term that determines the relationship between d of gx and d of hx for arbitrarily small positive values of x is the lowest degree term for which their coefficients are different. Since the lower degree terms up to L are the same for both G and H, the only term that matters is the L degree term, for which d of gx has a larger coefficient than d of hx. The second observation is that if little d of gk equals little d of hk for all k greater than some integer t, but little d of gt is greater than little d of ht, then the domination polynomial of g evaluated at x is greater than the domination polynomial of h evaluated at x for arbitrarily large x. Intuitively, as x gets arbitrarily large, the term that determines the relationship between d of gx and d of hx is the highest degree term for which their coefficients are different. Since the coefficients are the same for all k greater than t, and the coefficient for d of gx is greater than that for d of hx at the t degree term, then d of gx will be greater than d of hx for arbitrarily large positive values of x. What do these observations give us? They give us a way of determining whether one graph is more optimal than another, using just the coefficients of their domination polynomials, provided those coefficients meet one of the two patterns we discussed here, where they're equal up to or down to a certain term. Moving on, let's look at an operation that uniformly increases the domination polynomial of a graph over the positive real numbers, while not changing its number of vertices or edges, provided the graph satisfies a few criteria. Let G be a graph with n greater than or equal to 3 vertices and at least one isolated vertex x and at least one edge uv. Let G prime be the graph G without edge uv with edge ux, that is, the graph formed by deleting edge uv and adding an edge between u and isolated vertex x. Then d of g prime x is greater than or equal to d of gx for x greater than 0. If the second endpoint v of our original edge uv had degree at least 2, then we can also say the d of g prime x is greater than d of gx for x greater than 0. Note that all domination polynomials evaluate to 0 when x is 0. First, let's prove the first statement, which is that d of g prime x is greater than or equal to d of gx for positive x. Let S sub I be a dominating set in G of size I. Clearly, since G contains an isolated vertex x, that vertex x must be included in every dominating set in G. Next, selecting an edge uv and isolated vertex x, applying our operation to G in order to get G prime, and observing what happens to the I dominating set S sub I, one of 4 things happens depending on the dominating set S sub I. First, note that we'll refer to vertices or a set of vertices B as being dominated by another set A if all vertices in B are either a neighbor of some member vertex in A or are themselves members of set A. Case 1 is if both endpoints of our selected edge uv were in S sub I, then S sub I is still a dominating set in G prime. This is because S sub I already included vertex x, and the only edge that was removed from this graph was between 2 vertices that were already members of the dominating set. So by our assumption that S sub I dominated the rest of the vertices in G, it must dominate the rest of the vertices in G prime as well, meaning it's a dominating set in G prime. Case 2 is if the first endpoint, u, of our edge is in S sub I, and the second endpoint, v, is not in S sub I. Then if we take S sub I, include vertex v, and exclude vertex x, we get a new set S prime sub I, which is a dominating set in G prime. First, note that this new set has the same size as S sub I. Secondly, since it includes vertex u, which is adjacent to vertex x, and since it includes vertex v, we can say that S prime sub I dominates vertices u, v, and x. Thirdly, note that this new dominating set still includes all of the vertices that S sub I included except for originally isolated vertex x. So by our assumption that S sub I was a dominating set in G, it must be that all other vertices in the graph are also dominated by our new set, meaning S prime sub I is dominating in G prime. Note that this new set is not dominating in the original graph, because it excludes originally isolated vertex x. Case 3 is, if u is not in S sub I, but v is, then S sub I is a dominating set in G prime. This is because isolated vertex x must already be included in S sub I, and since our operation draws an edge between u and x, then u is dominated by S sub I in G prime, and v and x are certainly dominated by S sub I because they're members of S sub I. Also, since S sub I was a dominating set in G, then every vertex besides u, v, and x is also still dominated by S sub I in G prime. That means our operation does not change the domination status of the other vertices in the graph, so S sub I is still a dominating set in G prime. Finally, case 4 is if neither u nor v are in S sub I, then S sub I is a dominating set in G prime. The reason for this is that by the fact that S sub I was dominating in G, u and v must have been adjacent to some other vertex or vertices in S sub I, meaning they're still dominated by S sub I in G prime. Also, our operation does not change the domination status of the other vertices in the graph, so S sub I is still a dominating set in G'. It isn't too hard to prove that no unique dominating sets in G correspond to the same dominating set in G' that we've created according to our four cases. I encourage you to prove this yourself. What this means is that the number of K dominating sets in G' must be at least as large as that of K dominating sets in G, which in turn means the domination polynomial of G' evaluated at any positive x value is at least as large as the domination polynomial of G evaluated at that same x value. What we've just found is that as long as our graph satisfied the initial criteria, applying our operation produces a graph G' whose domination polynomial is greater than or equal to that of the original graph for any positive x value. We can take our conclusion one step further if the second endpoint of that edge had degree at least 2. If that's the case, it must have some vertex W besides vertex U that is adjacent to it. So if we have a set A equal to the vertex set of our original graph G minus both isolated vertex X and vertex V, then we have created a set that is dominating in G' but not dominating in G. The new set A is not dominating in G because it excludes the isolated vertex X. Since we already showed through our four cases that we can match each dominating set of size I in G to a unique dominating set of size I in G', the existence of a dominating set in G' that does not correspond to one in G through our four cases means that we actually have more n-2 dominating sets in G' than we do in G. This means the coefficient on the n-2 degree term is greater in D of G'x than in D of Gx. And since the coefficients of all terms in D of G'x are greater than or equal to the corresponding coefficients in D of Gx, we can conclude that for positive x, D of G'x is greater than D of Gx. Now that we have this result, let's explore a new theorem about optimal graphs, keeping our most recent result at the top. Let G be a graph with n greater than 3 vertices and E greater than or equal to the ceiling of n over 2 edges, as well as at least one isolated vertex. Then there exists a graph H sub R of the same order and size with no isolated vertices, such that D of Hx is greater than D of Gx for positive x. To prove this theorem, remember that R is the number of isolated vertices in our graph, and let G star be the subgraph formed by all the non-isolated vertices in G. Since G had at least the ceiling of n over 2 edges and n vertices, G star has n minus r vertices and the same number of edges as G. Next, we want to show that some vertex in G has degree at least 2. To show this, first assume the contrary, that all vertices have degree less than or equal to 1. Then the sum of the degrees of the vertices in G is at most n minus r, as the r isolated vertices all have degree 0. However, in a simple graph, the sum of the degrees is always double the number of edges, so that means 2e is less than or equal to n minus r. Yet e is greater than or equal to the ceiling of n over 2, which implies that 2e is greater than or equal to n. That in turn would mean that n is less than or equal to n minus r. Yet r is positive because we define there to be at least one isolated vertex in our graph. We found a contradiction, so there must be some vertex in G that has degree at least 2. Now, recall the part of a result that also mentions a vertex of degree at least 2. We can apply this part of our previous result to obtain the current theorem we're trying to prove in the red box. Let's assign the name V to a vertex with degree 2 or greater that we prove to exist in G. Then let's pick some vertex U that's adjacent to vertex V. Also, let's select any of G's isolated vertices to be our isolated vertex X. See where we're going with this? We're going to apply our operation from before to G, using edge UV and isolated vertex X. When we do this, we obtain a new graph, which we'll refer to as H sub 1. And by our previous theorem, and the fact that the second endpoint V had degree at least 2, we know the d of H sub 1 x is greater than d of Gx for positive x. Meaning we just produced a graph with increased domination polynomial over the positive real numbers. That's not all though. We can apply this operation iteratively to increase the optimality of our graphs while keeping them with the same number of vertices and edges, so long as we can find an isolated vertex and an edge between two vertices where one of them has degree at least 2. And since we're not changing the total number of edges in the graph by applying this operation, the same degree sum argument as before holds to guarantee the existence of a vertex of degree 2 in each graph obtained by the successive application of this operation. The only limiting factor in how many times we can apply this operation is the number of isolated vertices, as after each application we get one fewer isolated vertex. When we finally run out of isolated vertices, after r iterations, what we're left with is a graph H sub r with no isolated vertices, and that is more optimal than the original graph G, and also more optimal than any of the intermediate graphs we created with our iterations. Let's step back and take that in. We just proved that if a graph G satisfies these criteria, then there exists another graph with no isolated vertices that is more optimal than G. Alright, let's move on to the last concept in this video. We can apply the result we just found to make a definitive statement about what graphs are optimal in certain sets of graphs. Remember that G sub ne is the set of graphs with n vertices and e edges, and that the unique optimal graph is essentially one that's more optimal than any other graph in its set. Now, for the set G sub ne, where n is greater than 3 and e equals the ceiling of n over 2, the unique optimal graph is either nk sub 2, that is the disjoint union of n copies of the complete graph on 2 vertices if n is even. Or if n is odd, then the unique optimal graph is the disjoint union of n minus 2 copies of the complete graph on 2 vertices, with the complete bipartite graph k sub 1, 2. This is because, by our previous theorem, if our graph had any isolated vertices and the ceiling of n over 2 edges, then there must be a graph with the same number of edges and vertices that's more optimal than it. So the most optimal graph in this case cannot have isolated vertices. And the only graphs without isolated vertices, with precisely the ceiling of n over 2 edges, are the ones I just described here. Intuitively, this is because we just barely have half as many edges as we do vertices, so we can really only pair the vertices up with each other in components of k sub 2, as otherwise we'd have too many edges in one place and isolated vertices elsewhere. That's it for this video. I've left links about optimal graphs for domination polynomials in the description. There's a lot more to this topic, and I encourage you to investigate it on your own. In future videos, we'll take a look at other graph polynomials. Thanks for watching. Please subscribe, like, share, and comment if you liked the video. Have a great day.